Yeah, so let me just open this. Yeah, so I mistakenly wrote SMTB, right? I should have written SMTH00. So from what we'll be focusing on today, we'll be looking at the derivatives of trigonometric functions. So I believe that last time on your last test, you this was part of the scope, right? That was included. So we're gonna be looking at some introduction, then we look at the derivatives, then there are also exercises that you'll do. So based on the derivatives, first we're gonna be looking at two derivatives that are based on first principle. We're just gonna look at two derivatives which are based on first principle. So the first one, which is the derivative of sine x. So when we are working with the derivative of sine x, we're given a problem. They say let f of x be equal to sine x. Then we must find f prime of x. So every time you're given a problem like this, then you're supposed to use first principle. Now, the first thing that you're supposed to do is to state first principle. So the question is, how do you state it? Is you just write this formula. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h, right? Then what happens now is that we know that since we're given sine of x, what we're supposed to do now is that wherever you see x, you're going to substitute x plus h. That's why here we have sine of x plus h, and now the function remains the same here, minus sine of x. And we know that from the compound angles, this can be expanded to be sine of x cos of h, right? I mistakenly added this h, this 2. So we have sine of x cos of h, plus the sign doesn't change whenever you're dealing with the sign. Remember that the sign doesn't change. So we're going to have sine of x cos of h plus cos of x sine of h. So we're just going to change this when we come here. You see, right? Then we subtract that sine of x. Now from this stage, from this step here, we see that for us to proceed from here, we must look at the common factor. We have sine x, sine x, so we can be able to factor out that. So we can factor out this sine x to have cos of h minus 1. This will leave out 1. That's why here we have cos of h minus 1. So we'll just ignore this h which I mistakenly added here. So now this will be plus this, which is cos of x sine of h. So when we come here, we can now divide both sides by h. I can divide this one by h, divide this one by h. That's why here they're separated. We see, right? Then I separate them by this plus in between. So I'm sure that this we know this. We have learned this from the basics of I think it's from primary school, from grade 4 and so on, how to divide like this. So since I've taken this, take this as one thing, then I divide both sides by h, then they'll be separated, right, as I said. Then from here, if I apply the limit here, we know that we have two properties here. So if I can erase this, I can write the two properties that were introduced to when we come to trig limits. We have the limit, remember from trig limits, you have the limit as h approaches 0, I'm just going to use h, right, of sine h over h, which this is 1. We agree, right? And also the limit is h approaches 0 of cos of h minus 1 all over h, which this is equal to 0. Which also I can write 1 minus cos of h there. It's the same thing. So if I apply the limit here, I'm going to get 0, which is this. And if I apply the limit here, I'm going to get 1, which is this. You see, right? Then that's why from here, given that we ignore this h, right? So from here, we're going to be left with sine of x times h plus cos of x plus 1. Cos of x times 1, which this will give us cos of x. And we know that the derivative of sine x is cos of x. So thus f prime of x is equal to cos of x. So now coming to the second problem, where we need to derive cos of x using the same approach. Now when we come here to cos of x, we are given that they say let f of x be equals to cos of x, then find f prime of x. For us to find this f prime of x, we must use first principle, right? So I said that now we are only using first principle. So first we state first principle, which we write this. And then we know that wherever we see x plus h, we're going to substitute. Wherever we see x, we're going to substitute x plus h here. That's why here we have cos of x plus h, and then minus cos of x. But if I expanded this, remember just that I skipped that step here, right? Because of some space down here, they will not fit it. So when we see this cos of x can be expanded to be cos of x, cos of h. Since this sign is plus, on cos we change the sign. Minus sine of x, sine of x, sine of h, right? Then I subtracted that cos of x. We check that we have some common factors cos of x. That's why I factored out cos of x. I factored it out. Then I'll be left with cos of x minus 1. We see this right now. Then also we're left with this to be alone. So from here, we are given that if I come and say that now I'm having minus sine of x as sine of h, then I can have this. I can have that this was supposed to be, let me check, this is supposed to be positive. I mistakenly change the sign there. So we can have this, that since I factored out this, right, I have this. So I just put them like this. Since this one is a negative, I'm avoiding using brackets. So if you want, you could still factor it out like this. You have cos of x, you have cos of h minus 1, minus this one here, minus this one. And then you have minus sine of x, sine of h. You can still write it like this, right? Which is the same thing. So I just took this, put it first, then take this one, put it on the other side. That's why here I realized that the sign, I made a mistake there on the side. So now from this, now I divide both sides like I did on the other side. I divide both sides by h, right? So I'll have plus in between. Divide both sides by h. Then if I apply the limit here, we know that the limit of this will be 1. The limit of this will be 0. We agree there. So now if I come back to say that this, let me erase this. Yeah. So if I come back to say that since this is 1, I'm going to have minus sine x times 1 plus, this, don't forget it's plus cos of x times 0, which this will give us minus an x. Thus, the derivative of cos of x is equal to minus an x, and that we know. We agree, right? So now if I do this, now let's come to the next one and we look at the other problem. So if you have a question, please make sure you can just stop me and then you ask. Also, I'm sure you can see my screen here. I can't see the comment sections. So if you type on the comment sections, I can't see anything. Now we come to these ones. We come to the derivative of tan x. We're given if f of x is equal to tan x, then find f prime of x, which is equal to sec squared x, right? And then now from this one, you can still use first principle, or you can use quotient rule, right? But I avoid deriving from here to here, straightforward. Should avoid that. So now, using quotient rule, we must first change this tan x to sin x over cos x. I'm sure we'll see this. Must first change this to this. Then we use quotient rule. We agree, right? By quotient rule says that either we're given sin x over cos x. Quotient rule says that we are going to derive the numerator first. Is that right? This is a rule. Always, it's always the case. You derive the numerator first, you times by the denominator, minus, you keep. Now it's like you're doing the opposite. Now you keep this one and derive this one. Is that right? You're just exchanging their places. Then now you have that. Minus, you keep the sign, you derive the cos. All over, you square the denominator. So if you find that this one is more difficult to use, right? Some they prefer saying that if I have f of x being equals to sine x over cos x, so we can just have our sine x as g of x, or since we're used to having the denominator as g of x, we can have this one as h of x. We have the denominator as g of x. Right. In other words, there you just let h of x be equals to sine x. You let g of x be equals to cos of x. And we know that from this, if you are given f of x, right, which is equals to h of x all over g of x. Quotient rule says that if you want to find f prime of x, you must first have h prime of x, or what you can do, you can write it like this. Usually I tell people to write it like this. You just multiply them both here, you subtract, also multiply them both. Always tell people to do this. Then you square the denominator, right? And then what you must know is that on the one which is always the numerator, you must put a prime here. Then on the other side, you put the other one, the prime. So what you're just going to do now, you're just going to find h prime of x, find g prime of x. Then you come and plug them here. So in other words, for me to, this will be simple. I'll just have h prime of x. H prime of x, in other words, when I derive sine x, we know there that when we derive sine x, we get cos x. We've proven it there using first principle. Then when I derive g of x, I'm going to get minus sine of x, right? So I'll just come here and plug this, and I know that I need to also square the denominator, and the denominator is what? Is cos of x, so this would become cos squared x. You see, you just come in and put them here, and then you simplify, things become simple. So you can also do this, it's up to you. At the end of the day, you get to the solution, right? You're still correct. So now let's look at this problem. So now we realize that we can have that derivative of sine of x times cos of x minus sine of x times cos of x all over all over cos of x squared. So when I derive sine of x, I get cos of x. And then when I derive cos of x, I get minus sine of x. Make sure to put brackets, right? Avoid putting a dot only. That could be a problem. So when I multiply these two, I'm going to get cos squared x times sine squared x. And we know that these are written as 1. This is equals to 1. So you can have cos 1 over cos squared x, which is equals to sec squared x. Or someone can decide to say that this is, if I divide here those two like this, you are still correct, right? You would still be correct. Then this will be equals to 1 plus, we know that sine over cos is tan, right? So this will be tan squared x. And we must know that tan squared x plus 1 is equals to sec squared x. You see, right? This will still be correct if you were to do this. Then that will be the derivative of a tan. So now if we come to the next, which we have here, we're given, they say we must derive must derivate the derivative of cot x. If we are deriving cot x, we can also use quotient rule, because we know that cot x is the same as cos x over sin x. Like, it's just the inverse of tan x. So now we check here, we say that now since cot x is equal to cos x, we know that we can use quotient rule, as I said. And first, we know that we must always derive the numerator first, right? We must first derive the numerator first, then we keep the denominator. So now we subtract, so we derive the numerator times the denominator. We subtract the denominator with times, we subtract the numerator times the denominator. So we're just doing the opposite. First, we derive the numerator, we keep the denominator. Now I do the opposite. I just solve them, right? Or you do as I showed you on the previous example. So now, when we derive cos x, we know we get minus sin x, and when we derive sin x, we get cos x. So if we factor this out, we're going to get minus sin squared x minus cos squared x. So I can just factor out the negative, so I can get this, which is equals to 1, right? So I can have minus 1 over sin squared x, which is equals to minus cos squared x. So you have that. Any question? Or if you want, you can just divide this. You are going to have minus sin squared x all over sin squared x minus cos squared x all over sin squared x, which this would be minus, this will be minus 1 minus cot squared x. And here we know that minus 1 plus cot squared x is equal to, we know that this inside is equal to cos squared x. So now you know, if you didn't know, right, that this is equal to cos squared x, this inside 1 plus cot squared x. So you must know those properties. So now we come to the other question. They say we must derive sec x. If we have f of x which is equal to sec x, then we must find the derivative of that, which is sec x tan x. Also, this will be very important when you come to integration. So you must know the derivative of sec x. It's going to help us when we come to integrating this. When you need to integrate this, you'll need to use this idea of its derivative. So now for us, we're going to use quotient rule. So here's what I'm going to tell you, right? Every time you're deriving tan x, cot x, sec x, cosec x, you must change them first. Unless if you're deriving sin x and cos x, those ones you use first principle. But if you're deriving tan x, cot x, unless if they said use first principle, you can also use it. But if they didn't tell you, you can use quotient rule. Is that right? Tan x, sec x, cosec x, cot x. You use quotient rule. So now we come here and say that we change sec x to 1 over cos x, right? And then since we know that it's like this, we're going to say here that f prime of x will be equal to, first we derive the numerator, right? We times by the denominator, minus we keep the numerator, we times by the denominator, right? The derivative of the denominator. Then we square the denominator. We agree, right? Then when we derive the numerator, we get 0 here. That's why 0 times cos x is 0. Minus, when I derive cos x, I get minus sin x. And this will give us positive sin x, which is this. And we can separate this too. When we separate the denominator, we're going to have this times this. And 1 over cos x is sec x, 1 over, and then sin x over cos x is tan x. Then that is the derivative of sec x. We can see that it is very simple. So, simple as that. So, now we have this problem, right? And then we're given, they say, if f of x is equal to cosec x, then we must find f prime of x. Also, this one, we must know its derivative because it's going to help us when we come to integration. We'll use this in integration. So, we use quotient rule again. Now, deriving cosec of x, we change it to 1 over sin x. We use quotient rule. Do the same thing. We derive the numerator first. We keep the denominator. minus, we derive the denominator, we keep the numerator, and then we square the denominator. Then this will be 0 because the derivative of a constant is 0. 0 minus cos x, because the derivative of sine x is cos x. Then from here we have a negative cos x over sine squared x. Then we separate these two as we did last time. We have 1 over sine x cos x over sine x, and 1 over sine x is cosec x, and cos x over sine x is cotec x. You see, right? Then that is the derivative of that. I'm sure we can see that it's simple. So this is simple as that. Now let's see. Now we have this here. This is so simple to a point that if they give you such a question in a test or an exam, they would be saying take these 3 marks, right? Because it's simple. Now when we see here, they say find f prime of x if f of x is equal to 5x squared plus 4 sine x minus 7 cos x. So what you're going to do here, you're going to introduce the derivative here. So here's how you're going to do this one. You have f prime of x. If I introduce derivative here, d over dx, I'm going to have this f prime of x. Then I introduce d over dx here. Get 5x squared plus 4 sine x minus 7 cos x. Then what I was going to have here is I was going to have this d over dx on each of these expressions, right? 4 sine x minus d over dx of 7 cos x. So if we check here, this is what we did, right? So now this is the second step there, which I showed. Now if you check, if I derive 5x squared, I'm going to get 10x. If I derive 4 sine x, I will keep 4 as a constant, derive the sine, I get positive cos. Then I keep the 7 here as a constant, I derive a cos, I get negative sine. Then at the end, this is the solution. We say, right? So whereas that is the solution at the end. So this would just be that simple. If they would give you a derivative of this function, they say derive this. I believe also this one, I believe they would want to give you 3 marks, right? So when we come here, the majority are having a problem with this one because they don't know that when you're deriving a function like this, or let's start with, for an example, let's start with deriving sine x. Remember, when you derive sine x, you get cos of x, but it doesn't end it there. You must times by the derivative of the inside. Our inside here is x. Whatever that is inside the sine is x. So this would be cos of x times 1, which is equal to cos of x. You see right now? And then if now we'll come and say now we are deriving sine 3x squared. What we would get here, when we derive sine 3x squared, we get cos. You see right now, 3x squared. But we derive by whatever that is inside, we times by the derivative of whatever that is inside, which is that. And this would give us 6x cos of 3x squared. You see right? So if we check here, that's what we have. We have 6x cos of that. If I was deriving the sine alone, then we times by that constant. You see right? So the derivative of this, we are going to apply this separately. Then you derive 8x squared, you get 16x. Then when you derive this, you are going to keep the 5 as a constant. You derive the sine, you get the positive cos with its inside, right? Then you times by the derivative of that inside. We say right? And the derivative of that is 6x. So we put it there. 6x times 5 state. So we put it first here. Now that is the solution. I'm sure now we know how to derive that, right? It's that simple. So now we come to this one. When we are deriving this one, right? We are used to what we call chain rule. So one thing I can tell you about the chain rule chain rule is just a combination of rules. So this is coming from exercises. You can see now we're on exercises. This is coming from exercises 1C, right? So when we're on chain rule, I just took some of the exercises there. I didn't take all so that you can go to some of the rest, right? So now when you're given this problem, when I can talk about a chain rule is just a combination of rules. So you must know that chain rule is just a combination of rules. We're just combining rules. The moment you find yourself using more than one rule, you are using chain rule there. Like here, we used more than one rule, can be considered as chain rule. So just that there are more complex rules, or there are more complex problems. Like this one, you must put it as, this one is not even complex. You can put it like this. So when you look at this problem, we realize that the first thing that we're going to apply here, it's power rule, because that's the first thing we come across when you're outside. You see right now. So when we come here, we change that to this function, cosec of x to the 1/2. Then when we derive this, we apply a power rule first. When we derive this, we're going to say, I drop the 1/2, I subtract 1 on the exponent, I get that. I keep it inside, you see. Then I times by whatever that is inside, the derivative of whatever that is inside. And we know that the derivative of this is what? Is minus cosec x cot x. We have done that. So I'm sure you can see why we had to do that before we come to this problem. So from when you're within such a problem like this, you can just write the derivative of this with one step. You don't have to show all of it, unless if they say derive it alone. But if it's like this, you can just show the derivative like this. You don't have to show all the steps. So from here, we now take this to the denominator. Remember, when we take this to the denominator, it's going to become this on the denominator. It's going to be, that is going to be, let me write it here. This is going to be, and this will be, let me see, minus, this will be minus cosec of x cot of x all over 2. When I take that to the denominator, it's going to be cosec of x to the 1/2. Here I just forgot the negative, the cosec of x. We see, right? So it's going to be like that. And then this can be written as this. So we see that. So that is the solution to this problem. If you have any question, you can ask. Then we'll see what we do about it. So now we are given this. When we come to this problem, guys, check this. Here now we don't have any exponents. So I can say that maybe brackets. I get brackets, they symbolize that if there's an exponent outside, you are approaching this question, you come and see that exponent, you were going to use power rule, you see. But here we don't have such exponents, we don't have any brackets. We just have two expressions. So this tells us that when there are two expressions, you check the sign between the two expressions. It's multiplication. Sometimes you realize that the expressions are like this over this. This you would use quotient rule first. But since we see this, there's a multiplication instead of division, or instead of plus or minus, we're going to use product rule because they are multiplied. With product rule, says that we're going to keep one. It's like you consider one as a constant, you derive this, you add, you now consider the other one as a constant, you now derive this. So it's like this. When I want to find f prime of x here, let's say I first consider I consider this as a constant first, you see, right? So it means that I'll say cot of 3x, then I derive this other one, then I add, then now I consider this as a constant, then I derive the other one. You see, right? So if we check, that's what we did. Consider one thing as a constant, consider this as a constant, we derive this. Now we do the opposite. It's like we're just swapping them after adding, you see. Now we consider this as a constant, we derive this. So from here, when I derive cot of x, we know that the derivative of cot of x is minus cos squared x. You see, right? We have done that. So if we check here, I can go back to show you the derivative. If you forget that, it's good to know the derivative of that. You can just write it aside, right? If you forgot it. The derivative of cot x, we have done it somewhere here. Here's it. Derivative of cot x is minus cos squared x. And derivative of cos squared x, of cosec x is minus cot x, cosec x. So when we come to this problem now, which one is it? It's this one. So what we do, we derive this, right? We get this. We times by the derivative of the inside. We get 3. You see right now. And then we keep this as a constant. Now we come here. The derivative of this is minus cosec x cot x. The constant remains there to both of them. Then we times by the derivative of the constant, which is 5. You see, right? Then we get this. When you simplify, if I simplify this, I'll have minus 3 first. I have cos squared x cot 5x. Then when I simplify the other one, I'm going to have the 5 first, minus 5 cot 3x, which is this, and then this 2. You see, right? Then we have that. And then this will be the solution to this. Now another one comes. Here's e, right? So here's e. So now when we come to this one, we realize that when they say we must find dy over dx if y is equal to cos squared x. When you come to this, guys, remember cos squared x can also be written as cos x squared. So in other words, when you come to this problem, you see the squared first. You see, right now. So it means that you must use a power rule. First, when you derive this, you must drop the 2. So that's why when we come to derive this, we drop the 2 first. You see, or it's best to use u substitution. You see here what I did, use u substitution. You let this inside to be u. Hey, u is equal to x squared plus 2 all over x squared minus 2. This simplifies things, right? So that you are left with this problem to be like this. Because deriving this would be simple. When you derive this, let's come. When you derive this, cos squared u, you just drop the 2, you subtract the 1 on the exponent. So you're left with 2 cos u times the derivative of the inside. So it's like this. Let me show you how to derive this first. Let me show you how to derive this. I should first show you how to derive this. Let's see, we have y is equal to cos squared u. When we want to derive this, right, we're going to have dy over dx. If I introduce d over dx both sides, right? Also here, introduce it. And remember, this is the same thing as this. So what happens here is this. I'll first drop the 2, I keep it the inside, I subtract the 1 on the exponent, I have 1, right? And then times the derivative of the inside. The inside here is what? Is the cos of u. We see this, right? The inside is cos of u. When I derive the cos of u, I'll get minus sine x. So I can just keep this as minus cos u sine of u times the derivative of the inside. The inside is u. And here we have let u be equals to x squared plus 2 all over x squared minus 2. So I can just come back here and substitute that u. Then I derive it. You see, right? Substitute my u here. Substitute my u here. Or I derive the u aside. You can just derive the u aside. You know that d over dx of u is equal to, you use quotient rule to derive that. You see, right now. And then we come and use that quotient rule. We're deriving the u here. When you derive the u, we do what? we derive the numerator first, which when I derive the numerator I get 2x, I keep the denominator. You see right now, minus, now I keep the numerator, derive the denominator. When I simplify the numerator, I'm going to get this. I believe that everyone knows how to simplify, right? You just simplify like that. And then from here, this will cancel this, then that one will give us minus 8x. Then we know that this is the derivative of u. So you're just going to come there and plug, right? So on our u, you can just plug this. This I couldn't plug because of the space, right? They couldn't fit there. So I knew that I was going to tell you that here you're going to plug your u, you plug your u, you derive here, you plug the derivative of u. And then you can just multiply this and this, you get positive 16. You take this to the numerator. You're going to get positive 16x cos of u sin u. So you know what the u is. You're just going to plug the u. So now let's look at this one, right? This will just be the last problem we'll look at, and then I'll leave the rest to you, right? You can see here we're on page 26 of 44. So these are just problems on the study guide. I just took them, then made solutions so that we can also look at them. So now we come to the exercise F. That one was E, I bet. And then from here, they said we must find dy over dx. When we come to this problem, guys, first, we realize that we're having two expressions first before we can think of other things. So it means that the first thing which I must apply there, I must use quotient rule first before I think of other things. So I'm going to come and use quotient rule. You see, I derive the numerator first, keep the denominator, derive the denominator, keep the numerator. Then I square the denominator. You see, right? So you know that when you derive this, you're going to use product rule. I've shown you how to use product rule. You're just going to first, let's say I keep 3 sin x as a constant, or I keep sin x as a constant. Let's say I choose this 2 like this. And let's say I keep this like this as a constant. Let's say I want to keep this 2 to be like this. First I keep the sin x as a constant, derive the 3x, I get 3. Now I keep the 3x as a constant, derive the sin, I get the cos. Then I keep this which I had kept there. Then I come to this one. When I derive this one, I've shown you how to derive such a case. It's a power rule first. You drop the 1 over 2, subtract the 1. Now you derive the inside, which is this. You're gonna get this. You derive the inside of this, you get 2. You say right. If you can try to follow through. So I'd request that everyone here tries to follow through, so that when you don't understand, you tell me that I don't understand here and here. Right? And then from here you can simplify. That's why you have to write simplify as needed. So this is quotient rule. So you can use it carefully. Make sure that when you say the reason I said use quotient rule carefully, because when you're simplifying, make sure you don't mess up the signs. You can simplify as you like. You can just multiply this. This will cancel this. You're left with the 3x there. And then, or you leave it here. It's fine if you want. All right. And then there. Now, what I want you to do right now, I want you to go look at. You can look at all these problems. Then you also look at exercise 1G, because I don't want the recording to be too long, right? I know that if we make the recording to be too long, people won't. They won't do this. They won't look at the recording, right? And then this is 1G. Okay, you can look at 1G. The solutions are there. You look at 1H. You look at 1I. Yeah, also included some implicit differentiation there. And then now, so what we'll be doing next, right? Let's look at implicit differentiation. So you can just look at the ones which I skipped here, right? Because I believe that they're all the same. You just have to follow the context. So when we come to implicit differentiation, on implicit differentiation, we are given, let's say they give us this problem. Now let's check here. Yeah. So we're given this problem. I just took the second exercise, right? We're given this problem. They say find dy over dx. So with implicit differentiation, what you're going to do first, you're going to introduce d over dx both sides. Introduce d over dx here. introduce d over dx here, which is, I've already written it there. So we're just going to go there and look at problem. So you introduce the d over dx both sides. When we look at the left hand side first, we derive 3x squared, we get 6x, right? Then we look at the right hand side. If I derive this 4y to the 3, I'm gonna drop the 3 times by the 4, we get 12. Then we'll be left with y squared. But we are deriving y with respect to x. That's why we multiply by dy over dx. So here it's like I'm deriving y with respect to x. So that's how you read it. You see right now. Then here it means that if this was w, this was going to be w. I was going to be deriving w with respect to x. So you must keep note of the variables. I say plus. Now when I come to this one is product rule, because there are two expressions multiplying each other. First I kept sin y as a constant, derive x squared, I get 2x. Plus, now I keep x squared as a constant, derive sin y, I get cos y. Then because this one, I was deriving sin y, I was deriving y with respect to x. But when I derive the 1, I get 0. That's why I didn't add that 0 here, because it's pointless, right? And then from here, what you can do from now is that I removed these brackets because they were not that necessary, right? So you can see what's happening. So what you can do from here, whatever that does not have dy over dx can be taken to the other side. Took this to the other side so that I can be left with these two, so I can factor out dy over dx. You see, when this one goes to the other side, it becomes negative. You see, right? Then I factor out dy over dx, then I divide both sides by this. Comes here in the denominator. You see right now. Then that is the implicit differentiation. So implicit differentiation is that simple, guys. There's nothing more into it. That's simple. 3 marks. So now we have this question, right? They say we must differentiate f of x, which is equal to cot of 5x minus 3. So we're just gonna introduce d over dx both sides. Then when we derive, remember when we derive cot x, we get cot squared, right? But here the constant is not x, it's 5x minus 3. So we must times by the derivative of the inside, which we're going to get 5. So the answer here would be minus 5 cos sec squared 5x minus 3. So this also falls into that question which those ones which we were doing before. So now we come to this one, we're gonna do the same thing. This is I've shown you this already. This is product rule. If you see two expressions multiplying each other, I'm going to keep one, derive the other, then plus do the opposite, right? So which is like this. So if we come here, I actually shouldn't have written this. I made a mistake and wrote that tan, right? So if we come here, I keep the sec, I derive the tan. You say, right? Keep the sec, I derive the tan. I get the cosec. This one is not supposed to be there, right? So I derive there the tan, I get sec squared x. Then here I derive the sec, I get sec x tan x. So this is going to be this plus sec to the 3x. So here I was not supposed to have this tan, so shouldn't have yeah. So if we have, let's check, if we factor out this will be fine. This will be the solution. So now we see that. Now you can simplify this as you like. It's up to you how you want to simplify it. So you can simplify it as you like. Now this I was supposed to say that this is equal to this is equal to, I carry sec squared x minus 1 is equal to tan squared x. Should have said something like this if I have this to the other side. So I'll fix this one and this one. So I was typing this with the code, right? So I'm just coding this down. Sometimes we make mistakes. So now when you come to this one, see right now. Now if we have this, remember this, you're going to change this to the exponent 1 over 2. So if we check here, we changed it to exponent 1 over 2. And I said that the simplest way again to work around this, you can let the inside be u. You see, you change that to 1 over 2, you derive like that. Then when you derive that inside, I get it's you. When you derive sin x, you get cos x. When you derive tan x, you get sec squared x. Then you put that to the exponent. Then this one goes to the denominator. I've shown you how it goes to the denominator. It becomes positive root. That's why here we have a positive root. Alright. Then we have that. This is as simple. I feel like these are just repeating themselves, right? If we can look at it, it is just repeating. Now we go back to implicit differentiation. Now, on this problem of implicit differentiation, we're going to do the same thing. We introduce d over dx both sides. So here I had to mix the problems a bit so that you don't, I know that people, when you are doing the same thing, it's like they cram, right? So it's like, let me just mix them so that you don't, you can see that questions can come in a different format. So, but you must be able to determine what type of a problem is this. So here I can see that this is what is implicit differentiation. Because I see y, I see x, but I'm supposed to find dy over dx. You see, right? Even here, they didn't tell us what to find. They just said derive this. You must know that you must find dy over dx. So, I introduce d over dx both sides. When I derive this side, I get 2x. Here I get 2y, but I'm deriving y with respect to x. I multiply by dy over dx. Here, it's the same as that, you see. So if you can check this just repeated itself. It was there before we got this, right? It was product rule. I first kept y, derive x squared, I get 2x, plus I keep x squared, derive sin y, I get cos y. Then I derive by, multiply by dy over dx, because I'm deriving y with respect to x. So, now, so when we check here, right, we realize that now I can remove this bracket, so I have this, right? Now I said that whatever that does not have dy over dx must be taken to the other side, which is this. Took it to the other side, it became a negative, so that I can factor out dy over dx here, which is this. So I divide both sides by this to come here. That's why we have this one in the denominator. So I'm sure that this is just repeating itself, just like the previous problem we did. So I'm sure that we'll see that this is as simple as that, right? So yeah, this will be the last part of the problems that we've done. So what you can do now, I'm gonna send this. As you can see that I took some questions from I took all these questions from the study guide, and also these are just exercises there on the tutorials. So I'm gonna send those which I didn't take for you to do, and also share this recording, right, for you to go through. Yeah, make sure and don't forget to subscribe there, so that when I share, you can see the notification.